Hello, welcome to our presentation on the replication of this paper, Natural Language Processing for Cognitive Therapy by Berger et al. Just a quick overview. I'll talk a little bit about the concepts for the paper. We'll look at the hypotheses, look at the results, some of the challenges that we faced, and then talk about reproducibility. So the first thing to understand is that schemas are kind of the main focus of the labels for our data. Essentially, certain patients can have maladaptive schemas that relate to negative views on themselves, their world, or their future. And that can be reflected in thought records that they write. So here are the 9 core schemas defined in 2015 by Millings and Carnelli. You can see some related to competence, some related to health, etc. And the thought records are a way to collect the free text. And we'll take a look at one here in a second. And the utterances, they use something called utterances, which is essentially just like a short sentence or phrase in the thought record. These are pre-processed as free text. And then we use 100-dimensional glove embeddings to represent the words in the utterances, and the utterances as average of word vectors. So here's a thought record. Essentially, without going into too much detail, the utterances start kind of here in the middle row on the right-hand column. So they don't like me enough to wave back. This is an utterance. And then from that point, the participant can choose to continue down the rows here, reflecting on their previous response in the row above. For instance, why would it be upsetting to you if they don't like me enough to wave back was a true statement, and that person says I may be unlikable. And so you can continue on down as far as you want as a participant. And this is known as the downward arrow technique, which will be important later. And essentially, the more rows the person fills out, the deeper their thought record is. So how the utterances are scored is that they're essentially given a rating from 0 to 3 for each schema. Here's an example. I didn't do very well at dieting. This manual label was given a 3 for competence, a 2 for health, and a 0 for everything else. So I didn't do very well at dieting is more determined to be related to competence and health than these other schemas. And so the hypotheses are that the first one is that natural language processing could be used to interpret thought records and form a determination of the underlying schema. So that we could use machine learning to sort of generate what would essentially be a manual labeling task to associate an utterance with these schemas. And then the second hypothesis is that the downward arrow technique converges, meaning that the deeper the thought record goes, the more likely the method is to correctly predict the schema. So the deeper a thought record, presumably the more accurate the model would be. And then the fourth hypothesis, I'm not going to go too much into it because we didn't decide to reproduce it, but it essentially correlates active schemas with various mental health questionnaires related to depression and anxiety. And so here are kind of the results of our 4 models that we were able to get working: this k-nearest neighbors classification, regression, support vector machine classification, and regression. And the numbers here are related to the average Spearman correlation across the schema for this model. And you can see that some of these schemas are better represented by some models than others. For instance, the nearest neighbor classification does a much better job at classifying utterances in terms of the health schema than, for instance, the regression support vector machine, and so on. And actually, there's not a super clear difference between the models here in terms of which one would be better overall. Which is not the case for the original paper. The original paper, they used recurrent neural networks, which we were unable to get working, and those actually performed much better than the shallow methods that we used. They also included confidence intervals here, which we omitted for simplicity. So why is this? Well, the recurrent neural networks were fairly difficult to re-implement. We were able to implement the multi-label model, but not the per schema model. And the multi-label model didn't give us very good results, so I just left it out of the table for this presentation. The per schema model had bugs, and because there was a 16-hour computational time for this model, it was difficult to solve. For the second hypothesis, we essentially take all of the utterances at a given depth. For instance, this first element here is a depth of 1, depth of 2, depth of 3, and so on up to a depth of 12. Really, these later depths are not very useful because there's so few of them. By the time we get to depth 6, there's only 26 utterances at that level. And similarly, for depth 12, there was only 1. The first 3 to 4 are probably the more have more utterances associated with them. But it didn't appear that when we look at the Spearman correlations across those, that there was any sort of correlation. I ran a linear regression for this correlation versus depth, and the R value was very low and not significant. For H2, it seems that they took together some, they took into account the nesting structure of utterances nested within thought records, and then thought records nested within participants, which is something I didn't do. But nevertheless, they came up with fairly, pretty much the same conclusion, is that steps at deeper level could not be scored better by the models. And that probably has to do with the lack of data at that depth. So difficulties for hypothesis 2 was that the original code was designed to use the per schema model to determine the second hypothesis. We couldn't get that working, and it was a bit of a task to restructure that to use one of the earlier models, one of the shallow models, which we did do and include in the file h2.py. I won't go into the details of why it was so challenging due to the time constraints for this presentation. But essentially, it wasn't designed to use the other models. In terms of reproducibility, I would say that this paper had an exceptional availability of the data, which is extremely useful. It was already pre-processed, well cleaned, and they also provided the models exported from the execution of their code onto the file system, which could help to optimize issues like a 16-hour computation time for the recurrent neural networks. Nevertheless, there was a few minor bugs that made it difficult in the code. And also, really only the first hypothesis was very well represented in their code. H2 was had a cursory appearance at the end, and H3 and 4 were not there at all. And that's pretty much the end of the presentation. So thank you very much for listening.